Okay, hello. I'm Tim Weaving, a PhD student at University College London, and I'm pleased to welcome you all to the 20th instalment in Comp Biomed's e-seminar series in collaboration with the Virtual Physiological Human Institute, or VPHI. The talk today will be given by Daniele Tartarini of the University of Sheffield, which he joined in 2013 as part of the Insigneo Institute for in silico medicine, with the goal of accelerating virtual physiological human multi-scale models by adopting methodological and technological solutions, particularly in the domain of oncology. Daniele's research spans grid and parallel computing solutions for bioinformatics, GPU computing for finite element methods, and software frameworks for multi-scale modeling. Now, in today's session, Daniele's talk will serve as an introduction to biomedical image registration and the parallel framework for image registration. This is the methodology by which medical imaging may be corrected for further processing and ultimately aid clinical diagnoses. Patient images captured at different times and via different media such as CT, PET, MRI, and ultrasound are susceptible to an array of distortions, due, for example, to variation between image capturing systems or physical movements of the patient. Now, before we begin, I'd like to briefly remind you that the session is being recorded and will be available on the Comp Biomed website and YouTube channel shortly. So please do use this to go back over parts of today's talk and others in the series, and maybe even share these e-seminars with your friends and colleagues. There'll be a Q&A session at the end of the talk, so please save your questions until then. Once the talk is finished, you can post your questions in the questions tab, and I will read them out to Daniele to keep the session running smoothly. Now, that's everything from me. I very much hope that you enjoyed today's talk, and without further ado, I'm going to hand over to you, Daniele.
Hi, hello everyone. So today I'm going to introduce you the following outline in my talk. This is a talk which is part of a two-talk series. So the second one will be given next year, will be more in detail on the second part of this talk, which is pFIRE. So I'm going to introduce you about image registration and give you an idea of the quality measures and cost function used in this process. Then I introduce you pFIRE, the parallel framework for image registration, and what is our effort in refactoring towards exascale, and then some examples of applications. So image acquisition is a very powerful diagnostic tool, and it's used by the doctors to investigate particular situation of the patient. So there are different technologies that can be used, and they depend on which type of tissue has to be investigated. For example, bones is better investigated with the CT scan, which is based on X-ray. So there is a range of possibilities, and that depends also on the physics involved for doing the inspection. So these technologies can produce different type of images. For example, MRI images. This is the images of the brain, and they're taken with different methodologies and technologies. So the MRI is a scan of magnetic resonance and precision emission MRI. It's another image generated which explains the function of the brain. So when we analyze these images, we have a multimodality number of images which can highlight different functionalities of the brain, different information in the brain. Currently, the machines couple different technologies together. For example, this image is obtained coupling the CT scan with MRI in the same machine. It was not always the case. And in the past, you had to have a scan in one machine and then another one. And then the two images need to be overlapped in some way to get the same information. Image registration can be used exactly for this purpose. So let's say you have a position emission image and a CT scan, and you want to see what happens in a part of the brain and overlap with the morphology of the brain obtained by the CT scan, you need to use image registration. It's not the only case. So the other cases for image registration is when the one I showed you now is a multimodality registration, or in the case where the patient moves inside the scanner, so you have a different session when you have one scan of the patient, then you do another scan later, or you do with another modality, and the two images are not aligned. So to analyze the two images, you need to overlap them. It's also possible that you do a time variant analysis. It means that you acquire images at different time steps. So when you do that, there could be movement inside the image. So you don't have good information if you don't register, if you don't overlap correctly the two images. It is also the case that the patient develops some disease, some lump that they grow, and you want to see the evolution of this disease in time. So all the images captured need to be aligned properly. Also, there could be problems in the scanner that can generate some geometrical distortion and some problem with calibration. Last but not least, you can use the registration to overlap some modeling technique, like meshing of some part of the organs. Let's see an example. On the left, we have a CT scan of a thorax, and this is an image which is taken as a reference from the patient. Then assume that you have another image where the patient moved for some reason, and now you cannot compare what happened in the two images because you cannot. If you overlap these two images, you are not able to match the different region. So what image registration does is try to find the mapping function that allows you to move the image and overlap it to the reference image. The problem can be seen another way. So if you plot the two images into different color channels, you can see in green the fixed image, or source image is called sometimes, and the move image. Clearly, you are not able to compare the different part of the image because they're not overlapped correctly. So you need to you need to morph the second image on the first one to compare properly the different area in the image. If you look on the right, the function that makes this can be seen on a map. So if you remain in a mesh, if you see remember the previous slides, they were overlapped on the slides and mesh. So the arrows you can see in this plot, are exactly the displacement that allows you to map one image on the other one. If we generalize the problem, this can be applied in 3D, and you can have a 3D volume of the scan, and you need to find in the same way the mapping function that allows you to put in relation the coordinate, the 1 point, 1 voxel in one image to the other voxel in the other image. So if you think the image is just a function which says which is the intensity value of the image in that point. So F and M are two functions that say what is the intensity of the field in that point. So let's call the x, y, z the coordinate of the voxel in the fixed image, and x prime, y prime, and z prime the coordinate of the voxel in the moved image. We can write the equation of the translation of coordinate, considering the x prime, y prime, and z prime are just the coordinate, the original coordinate, plus some values. These values are the displacement. So the mapping is 1-to-1. What we need to find to register these two images are the values u, v, and w. For simplicity, we will discuss only about 2D images, but it applies easily to the 3D case. So the most simple mappings that we can have is the translation. So one image is just a translation of the other one. So what changes is just the addition of some constant. One image can be rotated and translated with respect to the other one. So we have a component of the translation plus the translation plus the rotation. Or we can have an affine transformation, which is, you can imagine the shearing of the image, which is an example of the CT thorax I showed before. The most interesting case is when we use nonlinear mapping. So we leave the freedom to U and V to assume any possibility, any type of function. This is quite similar, the approach of infinite element, to find the displacement when you apply some force to an object. So as usual, to find this function, you imagine to discretize the domain, so you apply a mesh, and then you want to identify what are the basis functions identified on the nodes on the mesh. So in this case, displacement along the x is given by a linear combination of the basis function multiplied by a value, which is the degree of freedom. We can apply different type of basis function. Usually they're polynomial. It could be bilinear or trilinear polynomial, depending if you're in 2D or 3D. It can be cubic, the order of the polynomial cubic, or Hermite polynomial. There are different possibilities you can use. So each function is each basis function is centered on the node, or on each node of the mesh, and the concept of partition of units holds. So it's 1 in the node, and then it's 0 in the neighbor nodes. So again, in 2D, the displacement allowed to put in relation the value of the images into corresponding pixel or into corresponding voxels. So these two functions, the displacement, are functions of the coordinates. So if we write an equation, we have that the fixed image has the same value as the moved image computed in the x prime and y prime. So this is the fixed image on the left. This pixel here, which is magnified just for example, has the same value as this pixel here in the moved image, just considering the exchange, the function maps the two coordinates. Now we want to simplify things or complicate in some way. We can expand this equation using a Taylor series. So you have the equation, and then this is expansion Taylor series. We recognize the derivative and the u and v functions. Then there will be higher order terms which are ignored, and then we'll have an impact, and we'll see later. So the registration equation becomes the following one. The important thing is that you will notice that the u and v functions now, due to the derivative, are outside of the m function. So this simplifies the solution of the problem. Clearly, as we apply the finite element method, we need to express the displacement as a linear combination of the basis functions. So degrees of freedom A and with respect to x and with respect to y, and the two displacement function u and v. So the registration equation becomes again as before, but we're just expressing explicitly the degrees of freedom. So there will be one equation for each voxel or each pixel of the image. Then we have we can express everything in a matrix format, and usually this equation is overdetermined. So there are more values of truth with respect to the degrees of freedom. And we can solve as usual way, inverting the matrix, and the solution of the displacement is the following. What is important is that this problem is ill-posed and ill-conditioned. The reason is that the T transpose matrix times T is almost always singular. It means that this solution is sensitive to noise, which means that noise introduced in the image can generate different solutions. So to solve this problem, as usual, can be used another constraint. And the way to go usually is to use a Laplacian to impose the smoothness. So the Laplacian can think about the second derivative. This becomes in the discrete form, comes in discrete form with the constraint L, Laplacian matrix, multiplied by the degrees of freedom. The new formulation we arrive is the following one. And we can solve with respect to the degrees of freedom. And clearly, since we expanded the equation in with a Taylor series, and this is accurate only for small displacement. So when displacement are larger, there would be more error. There would be we come back to the ill-posedness of the problem. So an iterative solution is applied, and as always, when we have iterative solution, we need to find the stopping criteria when we say that we are okay with the accuracy of the solution. So there are two different types of cost function quality measure that can be used. The first one is the more intuitive, the sum of square differences. So basically you compute the sum of the square of the difference between the fixed image and the moved image in the same point, in the same in the corresponding coordinate. Another measure is the Moodle information. Moodle information is a concept that comes from the information theory and is considered a golden standard for measure of image similarity. The problem with the first approach is that it is computationally efficient, but is sensitive with respect to the intensity different in the image. If you want to interpret qualitatively this concept, is that you can have the same image with two different level of gray, but it's the same content. If you compute the difference between the two images, you will have a value instead of having 0. So just changing the maximum of the gray level, you will have an error. So one solution for this problem is to use the binary image. As particular case of binary image, you will find this described in the paper of Rodos and Berber. And this concept is that if you think of a function, 2D function in 3D, you will have a surface. The binary image, instead of having a surface, will have a stack of value that till reaching the surface. So in this plot, imagine that it is a Gaussian function, and this has been the corresponding binary image. So this binary image, you will have a third coordinate, which is the intensity, but the intensity particularly is not the value of the intensity, but is a stack of value equal to 1 till the actual value of the function. We will not go into detail with this approach. This requires anyway another constraint that has to be, you need to have smoothness. You have to impose smoothness on this image such that you can have a unique solution in this with this problem. The registration equation becomes the following one, but we will not go into detail. We will consider, for our interest, the Moodle information. So the other criteria is Moodle information. This is a measure of independence of image A versus image B, considered as the distance between the joint distribution of the joint distribution and the distribution associated to the case of independent image. This formulation is from Kullak-Leibler and is the formula as shown before. So it's the sum of A and B are gray values, intensity values in the image A, intensity value on the image B. PAB is the joint distribution of these two values, and this comes from the information theory. Some of you recognize the formulation of the entropy, but we will not go into much detail about that. So considering the intensity values in corresponding voxel pairs, the mapping is maximal when the images are geometrically aligned. We'll see later an example, so it will be easy to understand. So the power of this formulation is that there is no assumption regarding the nature of the relationship between the image intensities. So this can be applied, for example, in multimodality images. When you have an image in colors that shows the functionality of the brain, for example, another CT scan, and you want to register the two images. This approach is considered golden standard, but is computationally very expensive. So what we are talking in the concept, in the formula we showed just now we are going to view what is the meaning on these values. So if you take an image and you plot the histogram on the image, you will have, in this case, is a 8-bit image in grayscale. So the values are between 0 and 256. So this histogram shows the count of the number of values for each gray value. So the probability of having gray value A for the image A is given by the normalization of this histogram. What is the joint histogram? So let's start considering these two images on the bottom. If you overlap them, you will have one pixel corresponding to another one pixel of an image, let's say this one, corresponding to the other pixel in this other image. These two pixels will have two different gray values. So what is the histogram of all these couple of gray values? So if you count all the different couples of gray values associated on the two images overlapped, what you will have the joint histogram. So for example, if the image A, this is the histogram of image A, the gray value A is associated on the other image B to the gray value B. So in this case where the two images are identical, so that is the same image, so if you overlap them, they're already registered, so it's the best possible case, you will have the same number, the same distribution in the histogram, so the joint histogram will be along the line. So if you imagine that you want to register two images, this is the best scenario. So the two images are, when are perfectly registered, the joint histogram will be aligned. But as you can imagine, this is not always the case. It is not the case. So let's assume an example. Let's see an example where we have the MRI scan as a reference, and the same MRI scan rotated by 15 degrees. So what will happen is that the point will not correspond exactly the one to the other. So this white here will not correspond anymore to this white here. So if you overlap the two images, it will be another gray. So if you look at the image, there will not be anymore the lines, the straight line which associate one value with the exact same value on the other image, but you will have a distribution of values. The more you complicate the thing, the more you rotate the image, the more the mapping between the two images will not be aligned. So you are adding entropy to the image. You will see that the more you rotate the image, the more the entropy around the diagonal line augment. So you will see that the different value distributes more around. So if you invert the process, you imagine you want to register these two images, you will know that they are not registered, but if this is easier to simplify here. So if you have a reference image, and these are the images at different rotations, so from 5 degrees to 30 degrees, if you imagine you want to register 30 degrees to 0, you imagine that at some point the registration algorithm will rotate or try to map this image to move the image to the fixed image. At this point, the way to check the stopping criteria is looking at the Moodle information, which is the result of the formula I showed before. So as you can see here, if the two images are aligned, so 0 difference in rotations, so perfectly registered, the Moodle information is the higher. The more the images are rotated, so the more are distant the one from the other or from the registration, the higher is the lower is the Moodle information. So the criteria is to find the maximum Moodle information. Maximum Moodle information means the image is registered. Now let's talk about the pFIRE. pFIRE is a software which is developed in Sheffield and is derived by some research done by Rod Dawes and David Barber. pFIRE implements the iterative algorithm we saw before and implements it using the Moodle information. So in two different parts of the algorithm, the Moodle information is used to decide which is the stopping criteria in the iteration algorithm. This software uses the algorithm underlying this software when you want to solve this system. As in finite element, you need to use a solver. So the A value, the degrees of freedom in the formula, the registration formula showed before, they need to be solved. So we adopted the Krylov solver. And this software is developed with an eye to optimize for HPC computing. So is developed in MPI. And there are a number of implementation, the optimization that can be done and need to be accounted to augment the efficiency of the execution. So in CombBiomed, we follow what is the incubation program. So the first step we went through is to try to optimize the registration algorithm and add other functionality to the original software, which is the possibility to choose different parameters, a different approach to register the images. We also recognize the importance of involving the users in this process, kind of co-design of the software. The reason behind is that the validation of the image is a complex matter, and the eye of the expert in the field can be of high help. The second stage in this program in CombBiomed is to make the software the best possible product. So we strive to fulfill all the software quality assurance criteria in the standard, and also respect what is the FAIR software, so findable, accessible, interoperable, and reusable criteria. And we want to have the software reproducible and reliable. I will show you how we dealt with this approach. So what we have done to achieve these results. At the moment, we are between the fast track and the deep track. So the next stage, we already started actually, is to optimize the parallelization of the software and deploy the software on cloud HPC. The last bit of the transition will be to enable this software to run on next generation exascale architecture. So to fulfill the requirement for the fast track, we created a set of solutions. So we offer the software on GitHub, so it's versioned and is offered publicly with open source license. It's an Apache license. Then we have also the documentation, which is online, and is an open format and is delivered through the read the docs standard. And then we integrate continuous testing integration. So we use at the beginning Travis, and then we changed to Jenkins because we needed to test also the MPI implementation of the software, and also test the containerization that we did for pFIRE. So Jenkins offers more flexibility in terms of the possibility we can have in the testing. So currently, these are the reference for finding our software. You can find on GitHub. You can just search for Insigneo pFIRE. As I said before, we used Jenkins replacing Travis CI for continuous integration deployment. So the software is written using Boost test as a software for testing, for unit testing. And then there is a Docker developed benchmark framework to test for integration and quality registration for the images. The documentation is offered through the docs, and we will be adding a second section where we have developed also the UML description of the software. We distribute the software as a source code, but also we prepare the Docker Singularity images. This is a requirement for two reasons. First, to allow reproducibility of the software, distribute very easily, but also to involve the users and have their feedback since the beginning. So we are collaborating with the other partner in Insigneo, outside Insigneo, to validate the algorithm on a certain type of problems. We strive to use only standard formats. So for the images, we basically use DICOM, but also some of the images we can process also PNG, TIFF, and HDF5 for the registration data and the images as well. The main problem also for this type of software, numerical software, is that the number of dependency, as you can see here, is devastating, because there is a lot of dependency, a lot of version, and there are a lot of combination of the type of dependency that we need for pFIRE. We tried different package managers. We tried also SPAC. All the package manager have pro and cons. The only limitation is always in the goodness and the good willing of the maintainer to maintain proper package manager to allow to install and do not have problems. So our containerization experience is we initially used Docker, but Docker is the best solution, in my opinion, for workstation. And there was a problem. It's an ever-changing scenario. It changes continuously every month. When we started, there was a problem that you cannot use the root user for running MPI, while with Docker you needed to use the root user. Now they introduce also the rootless mode, so that could be solved the problem. We then moved to a Singularity, which can reuse what we've done with Docker. And the main reason is that Singularity supports has a better support for MPI. So it's been developed within having in mind HPC solutions. All these softwares can seem something strange, but this concept of containerization is quite old. Someone can remind chroot, Linux containers is more or less the same concept. Is evolved in time, but the basic concept is the same. The problem we had in developing these containers is that there are a lot of dependencies, and it's complex to generate from scratch. It takes a lot of time to generate from scratch all the software. So from pFIRE plus all the dependency and the operating system. So what we did is to decouple the three layers. So we have the OS layer, which is a container. It is included then in another container. So once you generated this container, there is no computational requirement for generating the other one, the library dependency container, which include this one. So once you generate the library dependency container, you can include this one in the following one. So there is no computational effort to generate this part, and you just generate the container for pFIRE. The good thing about this approach is that you can have several versions of these layers with different versions of libraries, different versions of operating systems, and you can have a matrix of combination and test all of them in the continuous integration system. These are all evolving technologies with limitations, and the problems are always behind the corner. We started to test the performance of pFIRE, and in this case, the early test we did they were on small scale images. and the speed up looks promising, but it was only on a subset of on a small case. We didn't end up using more memory that the one was required by a single node. So we use maximum 64 GB on a node of 2 Intel Xeon. So the registration is not just a process to register 2 images one to the other. There is another interesting application of this. So assume that you have, this is a kidney renogram, so it's a scintigraphy image. Let's say you have a reference image and a patient image. One of the problems in some assessment of patient health would be important to segment, so trace the boundary around the image. So let's assume, imagine that you have an oncology patient and you want to understand if the volume of the cancer is growing. So you need to find a way to trace the boundary, to segment the organ, or in that case, the cancer, and in time with different, with new images, new scan of the patient, you want to compare, realign the images and compare the size of the tumor. In this case, we're talking about the kidney. So we have a reference patient. We can find the best, the golden, say, assuming that this is the golden standard to segment this kidney. So then comes a new patient, or a patient at a different time step. This is the following scan. What you will do if you want to segment again this one? Could be a different operator doing again manually. So it will introduce error. One of the solutions could be to take this image, register to this one, use the mapping function to apply to the golden standard contour, golden standard segmentation, and transform this segmentation to the one of the patient image. So just computing the mapping, you can then reapply the segmentation to the new one, and you will have the segmentation for free without, let's say, operator errors. This is another application. You can find the full description on this PhD thesis of Angelo Longo. So this is a section of a vessel, and this is a series of images taken in 40 time steps. So heart is beating, the vessel changes size, and you want to know how much the size is changing. So you need to measure some parameters. So what you can do is to segment the first image, and then in time, when you have another scan with another sequence of image, you can register the new image to the moved image to the patient image, and then transfer the segmentation. So it applies in two different ways. The first one is you can just segment the first, you can consider the first time step as the reference image, segment it, and then register the next time step to the fixed image, and apply the mapping to segment the second one. Or you can do the same work for a different sequence taken in time or during another session with the patient. Another application, you can use the same method to transfer mesh that I used to model component part of the body. In this case, let's assume that you have a finite element model or any type of modeling that requires discretization of in this case, of the bone, and this is the spine. So it's the same problem that applies. You can find a way. There are a few works done by different groups, including Rodolphe, on the vasculature system, but you can register the two images find the mapping between the two images, so the registration mapping, and apply the same registration mapping to the mesh. So if you have, for the reference image, the optimal mesh describing, in this case, the spine, for every other patient or every other time step later, you can just register the new image, new patient image to the reference one, and applying this mapping, you can just obtain the correct version for the new patient of the mesh. This is an artificial image to associate qualitatively these two one. There is no work associated with this one. It's to explain how it works. There's plenty of other papers, but cannot be used for copyright reason here. Another application is related to the biomechanical properties of the bones. So the CT2S service, what does is to take two scans of the same bone, one in a relaxed scenario, another one subject to a tension. You will have two different images. If you register the two images, you will find the displacement, the registration function, but the registration function is just the displacement. So this data that you have, you can convert it and obtain the stress strain you need for the bone. So this is used by one group in Sheffield led by Enrico Dallara to assess the strength of the bones and the probability of fracture. So I'd like to thank all the group for the contribution to the work. And this is the team in Sheffield. And I'll leave you the floor for questions.
Fantastic. Thank you very much, Daniele. Just a quick reminder for the audience, if you have any questions, then please go ahead and write them in the questions tab so that I can read them out for you. Now, whilst we wait for the questions to start coming in, I've actually got a couple of my own for you. So in the presentation, you mentioned a few times that this theory scales quite easily to 3 dimensions, right? And we kind of saw it a little bit with the spine reconstruction there. So has this technique been successfully applied in the 3-dimensional case? And how big an impact is there on the computational resource to perform image registration in 3 dimensions?
Yeah. So far, our software has been developed for 2D. The 3D version is under validation, and the theory applies is the same. Doesn't change the formulation of the theory. So what you can see for the 2D images can be applied for the 3D images. The complexity is then the pre-processing or post-processing that you need to apply for these images. Let's say, for example, if you have a DICOM image that is not organized properly with all the scans, you need to find a way to organize the volume of data. So it is just a processing problem. Theoretically, it can be applied, and has been applied successfully. There are a few papers that has been published of other version of this theory applied before. So this theory has been developed in Sheffield by Rodoz, Dave Barber, and there is different papers describing this application even in 3D. pFIRE is inspired by this theory and is a new implementation of this theory from the papers.
Right, I see, thank you. I guess it seems mandatory at this point that I ask something with regard to the exascale. So, what is the current state on the path to exascale here, and do you plan to use any GPU computing?
So we have in mind, so this service here is based on MicroCT images, and they use the images from the diamond source light. And these images are really heavy, so they require a tremendous computational power. So we're talking that each time step can be in the order of tens of gigabytes. So the problem is that you need to allocate enough memory, and you have enough computing power capacity to solve the problem. Being a finite element problem and the solution is about solving matrix vector products. So generally, in the worst case scenario, there is an interesting accelerations of using GPUs with respect to CPUs. The thumb figure is that 1 order of magnitude, so moving to GPUs. The complexity is always to find the right optimization, a combination of settings to reformulate the problem in the right way to be run on GPUs. We haven't tried yet. The libraries we rely on, PETC, they have solvers implemented already in GPU. So this is some work we would like to do in the future, but we haven't done yet.
Sure, thank you for that. I haven't seen any questions come in from the audience yet. So I suppose I'll ask another one, and this isn't really fully formed in my head, I suppose, but it seems as though this technique is very much reliant on having a high quality target image, right? Is it always feasible that that can be attained? You know, how do you assess whether or not your target is true in a sense?
It really depends on the problem.
Sure.
So if you imagine that what is the pipeline, so you have some scanner that acquire information. This information depends on the technology used. So there is some limitation in the resolution of the problem itself, in the physical problem. Then this machine, they have a limitation in their own resolution. Then you process and you apply your solution to your methodologies to these images, and then you show these results on screens, which they have another type of resolutions. So there is the first problem, which is the transfer information between in this pipeline, and you need to take into account what are the resolution of the different stages. Assuming that everything's fine, the other problem, you have the maximum combination of resolution to obtain the right resolution to make the assessment, because that's what is important. The other problem with this approach is that the equation has been, there is a Taylor series inside the equation. So that includes some generation of error that has to be assessed. So to overcome this one, I found quite complicated to validate these algorithms, not this one, but in general the registration algorithm on images, because different images of different organs and with different modalities have different, let's say, resolution or meaningful resolutions. And it's difficult to compare one algorithm to the other one. So one thing we have in mind is to use some validation data sets that has been used in the public competition to compare the different approaches. And one approach could be also to insert inside the images. So use some data set where has been inserted the fiducial points inside the images, and then compare with the results to check if the registration is correct, considering the fiducial points. So I hope that answered your curiosity.
Yeah, it certainly does. Thank you. I still haven't got any questions from the audience, I'm afraid. So I'll ask you one more, and after that, if nothing else has come in, then I'll I'll draw the session to a close. But in principle, these image registration techniques, they seem to be kind of agnostic, right, to the underlying hardware. So in that sense, could these techniques be extended outside the medical domain, you know, for example, to processing astronomical images from telescopes, just as an example?
Indeed. I'm not familiar with this type of images, but I can tell you that this approach is used, for example, in fracture, so in civil engineering. So it's called digital image correlation. You can have, you can analyze, take a picture of, let's say, concrete under stress and then fracture. You can use the registration to assess the stress that this piece of cement has been subject to. So this is another application of this registration. You were asking for those images regarding the not segmentation, just for the registration, right?
Yes, indeed.
So usually, if I have in mind the image, the image with the stars, for example, you can imagine this image as a series of Gaussian functions. The complexity of registering is that if these are too distant, the problem, there could be a problem generated by the fact that there is a Tiro series underneath these algorithms. So if they are too distant and the shape of this function is not smooth enough, you can have some ill conditioning in the problem that you want to achieve the results you want. It needs to be tested, and I simplified the presentation, but there are different parameters of smoothing that can be used and changed, and some kind of introduction of memory inside the solution of the iterative solutions. So the algorithm need to, I would say, tailor to different type of images. And then that, I think, is the difficulty to translate on different domains. Even within the biomedical one, you can have different type. Let's say, for example, if you have a section of a bone, it would be different from having a transverse section of a bone. Say, if you take a leg, it would be easier to register a cross section with respect to a longitudinal section. But with the proper changes in setting the algorithm, you can achieve both.
Sure, I understand. Well, those are all of the questions that I had for you. There haven't been any more from the audience. So thank you very much for giving such comprehensive answers to those. I very much enjoyed the talk. So thank you once again, Daniele, for giving us your time today to speak about biomedical image registration. Just one final reminder that this e-seminar will be available on the CompBiomed YouTube channel and website, which is accessible. Well, if you, Daniele, could you just pop onto the next slide for me, please? So the YouTube channel and website is accessible via the link shown on screen currently. And then finally, thank you to everyone in the audience for attending, and I hope that you all enjoy the rest of your day.
Thank you for the invitation. See you.
Bye-bye. Thanks very much, Daniele.
Bye-bye.